Hello everyone. In this lecture we're going to talk about basics of modeling. So we are reaching the last part of BP13 and today we're going to focus on the solution of ordinary differential equations with application to radioactive decay. So that's basically the equation that we are going to solve. There is a rate of change of a substance and there is the amount of a substance here. We are going to study also the case of a chain decay, where uranium decays to thorium, which decays to radium. But first, we want to ask ourselves, what is actually a model? So, as usual, if you want an answer, you can ask Google, for example. And here are some important notions. So the first result is that a model is a three-dimensional representation of a person or a thing or of a proposed structure, typically on a smaller scale than the original. A second definition is a thing used as an example to follow or imitate. And I think there are some important words here is representation. Smaller scale may be applicable in modeling of earth science processes. And the key words here, follow and imitate. So these are some important notions here, but it's not exactly the definition of what we mean when we talk about modeling in earth sciences. So how does that apply to geosciences? I think a much better definition is provided on this webpage here. A model is not the real world, but merely a human construct to help us better understand real world system. So to understand a real world system, we construct a model. So we can construct potentially a smaller scale model that will be used to imitate and to imitate what is happening in the real world. So we need to construct something that we can study in order to understand the real world system. Some example of models are here. So you see, for example, a model of water drops here. It's not the real world. It is a simulation. So that's one appearance of a model. Another appearance of a model can simply be a diagram. So you see a stability diagram. So you have the stability number of a slope as a function of the slope angle. So that's very important because this type of diagram, they help us to understand the behavior of a system. So for example, if the mountain is going to collapse, sometimes the simulation is just there to produce a nice animation. So if you want to make a cartoon movie, like what you see in all the Disney or Pixar movie nowadays are based on simulations, so they make this kind of stuff. Understanding, quantification. So here you have a simulation of a subduction zone. You see a plate here, which is diving into the mantle, and the plate is deformed in the subduction zone. So that should be a kind of geodynamic situation with which you should be a bit familiar. So you see a stress pattern here in the subduction zone, and you see how the stress changes sign in the subduction zone because of the bending. And here we can clearly use this modeling to establish quantification of stress changes in the subduction zone. So that's one reason for modeling here. And another reason for modeling is a prediction. So you see here a prediction of the weather above Germany. So that is one real application of a model, the prediction of what's going to happen in the future. So here are the basic principles. The key features in common with the development of any model is that one, simplifying assumptions must be made. So we need to isolate and make some key assumptions in order to isolate the key processes. Boundary conditions and initial conditions must be provided. So if you want to study what's going to be the weather tomorrow, you need to know what is the weather today. And 3, the range of applicability of a model should be understood and stated. So of course you need to know what you can do with the model. There are different types of quantitative models, and in earth sciences, models for which the smaller scale notion really applies here are analog models. So these have been used extensively to study tectonics and geomorphological processes. And basically you go to the lab, you build a box, for example, a meter long box, in which you fill layers of sand, and you apply deformation to this layer of sand and to these layers of sand, and then you can obtain results which are depicted here. For example, a fallen thrust belt, where you see thrust zone and exhumation of material coming from the base of the wedge here. So that's a smaller scale model. It's an analog model. Then a model can be analytical. So analytical, it means that you first have found the essential or identified the essential physics of the model. For example, an ordinary differential equation, and that then you manage to solve for the quantity of interest. So here n would be a quantity of interest. You solve for n, and using this expression, so it's a purely mathematical solution here, using this expression you can predict the evolution of a system. So the mathematical model is solved analytically. So it's an exact model. But of course, it can only be applied to fairly simple physical systems. Then there are numerical models. And the numerical models are an approximation of the mathematical model, of the exact model. So we have an equation that involves dn dt, and we approximate it, for example, with finite differences here. A change of n divided by a change of time. And with this, we can construct another solution here, and it is an approximate solution. We come back to this. Why do we want to solve a problem numerically if we can do it analytically? There is no reason. But in many cases, we cannot do it analytically. So if you look at a subduction system, or the weather forecast, or a simulation here of water droplets, these problems are far too complex to be handled analytically and to be solved exactly with a mathematical method. So we need to apply a numerical solution of the underlying physical equations. So let's have a look at an example. So in this lecture, we discuss about an ordinary differential equation, ODE, and we apply this to the radioactive decay case. So what's an ODE? It's basically an equation in which you have a quantity and you have derivatives of this quantity, but these derivatives are all taken into one dimension. So here we have n, and we have the derivative of n with regard to time. So there is one dimension. In fact, it is time. Then we seek a solution of n through time, and we need to integrate the equation if we want to find n. So the ODE can be of higher order, so there can be different degrees of differentiation into this expression, and are used in many fields of physics or finance, risk analysis, biology. So all these are very common expressions. So the first thing to do, let's derive an analytical solution for n with t. So that's a fairly simple equation. We can try to find an analytical expression. There are several steps. So first, let's relabel the n dt n dot. So the n dt is equal to n dot. It's still equal to minus lambda n. And then we put n from the right-hand side to the left-hand side. So we have n dot divided by n is equal minus lambda. And then we integrate. So integrate over time, n dot divided by n, and integrate over time minus lambda. So the integral of the derivative of a function divided by the function itself is simply the log of n, and the integral of lambda, which is a constant here, is lambda t plus a constant. Now we want to recover n, so we apply the exponent to the log and the exponent to the right-hand side too. And then you can find this expression, n is equal epsk exp minus lambda t. We now rename xk by big K, and we have an expression n is equal big K exponential minus lambda t. That's an exponential decay solution. Now that we have this general solution, we need to define, to find the constant. And to find the constant, we will use here the initial condition. So the initial condition, in our case, we will state that n at time is equal to 0 is equal to a known quantity, the starting quantity, n0. That's known data. Using this information, one can solve for k. So we have k is equal n0. So you just plug this into this equation. So at t, time is equal to 0, exponential is equal to 1, and k is equal n0. That's how you get this. Step 9. Okay, you can use k is equal n0 in the general expression, and you get a specific solution now. N is equal n0 exponential minus lambda t. That's our analytical solution in 9 steps. Now let's make a numerical approximation of the evolution of n. So here we have one first order derivative of n with regard to t. So let's make a finite difference approximation. We change the derivative of n with regard to time by a ratio of increments. So delta n divided by delta t is now approximately minus lambda n. What is delta n? This is n nu minus n old. What is delta t? Delta t would be a model parameter that we will fix. So this is known. N old will be known. Lambda n, if we assume n is equal to n old here, this is all known. And we can find a solution for n new. And that's how the solution can be found. So we have n new is equal n all minus delta t lambda n The last thing to be done when we work with radioactive decay, you often hear about the half-life time. So what is the half-life time? The half-life time, it corresponds to the time after which an initial quantity, N0, has reduced by a factor half. So let's use our analytical expression. N is equal N0 exponential minus lambda t. Now we set N, we divide it by 2 because it had reduced by half. The time for which this happens is the half-time, the half-life time, t1 half. And now we want an expression for t1 half, so we can solve for t1 half. So let's do this. We solve for t1 half, and we get the expression 1 half is equal exponential minus lambda t1 half. Again, we want to recover the t1 half, which is in the exponential. So you take the log of both sides of the expression. Log of a half is equal minus lambda t1 half. And then log of 1 half is log of 1 minus log of 2. And this is equal to minus lambda t1 half. Then it's easy to solve for t1 half. It's simply log of 2 divided by lambda. So we have now a definition for the half-time, a mathematical definition for the half-time. Then what we will do in the exercise, we will display the analytical solution. So we will program the solution we derived in 9 steps. We will display the numerical solution. So we will program the solution we derived in 1 step. And we will depict also the half-time on the diagram. So this will allow us to model the evolution of the amount n as a function of time. And we will see a typical exponential decay curve. So obviously this is a simple case, and the analytical solution and the numerical solution will be in good agreement. So the analytical solution can be used to check if the numerical solution is correct. But as stated before, in many cases, it's difficult to derive an analytical solution, or sometimes just impossible. So let's consider a more complex case here. We will consider a case where we have a decay chain. So that's part of the uranium radium decay series. We consider this branch here. Uranium 244 decays to thorium 230, which decays to radium 226. So we have these substances, and here we have the time for the decay. These are the half times: 2.46 10 to 5 years, 7.54 10 to 4 years. So how to model this thing? There are basically 3 quantities that we are going to monitor: the quantity of uranium, thorium, and radium. So we need 3 equations. So we will consider the quantity of uranium that will decay with time. So here we have the quantity of uranium, the time, and here is the parameter lambda. Then we have the quantity of thorium, and the quantity of thorium decays to radium, but it will also be produced by the decomposition or the decay of uranium. So we have a positive source term, which is basically coming from there with a plus sign. So what decays from uranium is converted to thorium. There's a source term here. That is the decay of thorium to radium. So in the evolution of radium, we also have a positive term, a contribution coming from the decay of this one into this one, and the decay of the radium itself. So we have three coupled equations, one for the evolution of uranium, one for thorium, and one for radium. And they are coupled because the decay of this one produces an amount of this, and the decay of thorium produces an amount of radium. So in the exercise, what you will have to do is to enter the correct value for the half-time. So here you have this parameter, which is given here for the half-time life, and we will need to compute lambda from T half. We have derived an expression for the relation between lambda and T half a few slides before. So you will need to use this solution. And then you will compute the evolution of the amount of each radionuclide using the numerical solution. And finally, we will visualize. So we will get plots that look like this. On the one hand, you will have the quantity of uranium that decays, the quantity of thorium on another line, and radium on the third line. So in this lecture, we discussed some basic principles of modeling, and we applied it to the solution of ordinary differential equation. So for the simple case, we have considered both analytical and numerical solutions. And for the complex case here, like the multiple decay, we have only considered a couple numerical solutions. In the next and last lecture, we will discuss the solution of partial differential equations. Thanks for your attention.